The area under a curve. Approximation by sums of rectangle areas. Suppose we have a function f, defined on an interval ab, and suppose that f of x is greater than or equal to 0 on that interval. By the area under the curve, we mean the area that is bounded by the x-axis and the graph of the function between a and b. We'd like to calculate the area of that region. We begin by constructing approximations. Here's an approximation to the region consisting of 4 rectangles. Each rectangle here has width b minus a divided by 4, and the height of each rectangle is equal to a value of the function for some x along the base of that rectangle. Since this approximation uses 4 rectangles, we'll use the symbol s sub 4 to denote the sum of the areas of the 4 rectangles. If we increase the number of rectangles to 8, we have a picture like this, and we'll use s sub 8 to denote the sum of those areas. Here we have 16 rectangles. Here we have 32. And this is an approximation using 64 rectangles, which appears to be a fairly good approximation to the area under the curve. So the idea here is that the area will be approximately equal to s sub n if n is large. That approximation should improve as n gets bigger and bigger, and so we can say that the limit as n goes to infinity of s sub n should give us the exact value of the area. We'll now describe the general setup of an approximation using n rectangles and a uniform grid. By that we mean all of our rectangles will have the same width. So again, suppose we have a function that's greater than or equal to 0 on the interval ab. The first thing we'll do is divide up the interval ab into n subintervals with endpoints x0, x1, x2, x3, and so forth up to xn, where x0 is equal to a, the left endpoint, and xn equals b, the right endpoint. So we have n subintervals. Each one has the form x sub I minus 1 up to xi, where I goes from 1 to n. So in other words, we have intervals x0 to x1, x1 to x2, x2 to x3, and so forth. Each of those subintervals has the same width. We'll call that width delta x, and it's equal to the total width of the interval b minus a divided by n. We can also give a formula for x sub I. X sub I is equal to a plus I times delta x. So x0 is equal to a plus 0 delta x, x1 is a plus 1 delta x, x2 is a plus 2 delta x, and so on. Now we make a choice of n evaluation points, x hat 1, x hat 2, and so forth up to x hat n, where x hat sub I is in the ith subinterval. In other words, x hat sub I is between xi minus 1 and xi. These are the yellow dots that you see along the x-axis in the picture. We evaluate the function at each of those numbers to obtain heights for our rectangles. So we now have n rectangles, which we can label 1 through n, and we'd like to write down the sum of the areas of those rectangles. So let's consider the ith rectangle, which is situated above the subinterval x sub I minus 1 to xi. We have an x hat sub I in that interval, where we evaluate the function to obtain the height of that rectangle. So the height of the rectangle there is f of x hat sub I, and so the area of that ith rectangle is simply height times width, or f of x hat sub I times delta x. And so our approximation to the area under the curve is s sub n equal to the sum of those areas, f of x hat 1 times delta x plus f of x hat 2 times delta x, and so on. We can express this sum in a more compact fashion using summation notation. The uppercase Greek sigma here is a summation sign, and we read this as the sum of f of x hat sub I times delta x as I goes from 1 to n. Convenient choices of x hat sub I. If we choose x hat sub I to be the right endpoint of the ith subinterval, then we obtain what we can call a right endpoint approximation. The right endpoint of the ith subinterval is the number xi, and so we let x hat sub I equal xi, which is a plus I times delta x. And the resulting sum is s sub n equal to the sum as I goes from 1 to n, f hat sub I times delta x, where x hat sub I is a plus I delta x. If we choose x hat sub I to be the left endpoint of the ith subinterval, then we obtain what we can call a left endpoint approximation. This means that we're setting x hat sub I equal to x sub I minus 1, or a plus I minus 1 times delta x. And the resulting rectangle approximation to our area is the sum, as I goes from 1 to n, of f of a plus I minus 1 times delta x. Another good choice of x hat sub I, which results in what we call a midpoint approximation, is to take x hat sub I to be the midpoint of the ith subinterval. This means that x hat sub I is the average of xi minus 1 and xi, which we can write as a plus I minus a half times delta x. So just think of this as the right endpoint, a plus I delta x, minus half of delta x, which puts you in the middle of the ith subinterval. The resulting area approximation is the sum, as I goes from 1 to n, of f of a plus I minus a half delta x times delta x. Now let's look at an example. Let's consider the function f of x equals x squared on the interval 0 to 1. Here's the graph of the function, and here's the area under the curve. Let's compute left endpoint, right endpoint, and midpoint approximations to the area based on n equals 10 rectangles. N equals 10 gives us delta x equals the width of the interval, 1, divided by 10. Now let's begin with the left endpoint approximation. We'll compute the sum of the areas of the rectangles in the figure. We let x hat sub I equal the left endpoint of the ith subinterval, which here is 0 plus I minus 1 times 1/10. Notice this gives us x hat 1 equal to 0, x hat 2 equals 1/10, x hat 3 equals 2/10, and so on. The sum of those rectangle areas is S10 equals the sum as I goes from 1 to 10 of f of x hat sub I, which here is I minus 1 times 1/10 quantity squared times delta x, or 1/10. Now let's indicate how this calculation can be done on a TI-83 calculator. We'll bring up the list menu and look under the submenu Math and choose the function Sum. Then we'll go back to the list menu and look under Ops and choose the function Sequence. The rest is straightforward. We type in the formula 1/10 times I minus 1 quantity squared times 1/10, and then type comma I, comma 1, comma 10 to indicate that we want I to go from 1 to 10. Then we press enter and we find that the sum is 0.285. Now let's compute the midpoint approximation with 10 rectangles. Here we want x hat sub I equal to I minus 1/2 times 1/10, and so S10, based on this choice of x hat sub I, is the sum as I goes from 1 to 10 of the square of I minus 1/2 times 1/10 times 1/10. Now to do this calculation, it's convenient to simply bring up the previous entry and edit it by replacing I minus 1 with I minus 0.5. With that small change made, we hit enter again, and we find that this midpoint approximation is 0.3325. Now let's calculate the right endpoint approximation with n equals 10. Here, x hat sub I is simply I times 1/10. Here's the formula for S10, and we'll do this calculation by again recalling the previous entry, modifying it by removing the minus 0.5. We press enter and find that the right endpoint approximation is 0.385. Now let's indicate how this would be done on a TI-89 or 92 calculator. It's actually very similar, although a little bit simpler. The sum function on this calculator is represented by the sigma symbol, and the sequence function that's needed with the TI-83 is not necessary at all. So we simply type in the formula shown here, press enter, to obtain the midpoint approximation 0.3325. Now let's look at another example, this time involving the function f of x equals 1 over x on the interval from 1 to 3. Here's the graph of the function, and we'd like to calculate approximations to the area of the shaded region. Let's first use n equals 10, which gives us delta x equal to 3 minus 1 divided by 10, or 1/5. To compute the left endpoint approximation with n equals 10, we'll note that x hat sub I should be 1 plus I minus 1 times 1/5. So our sum, S10, is the sum from I equals 1 to 10 of f of x hat sub I times 1/5. Notice that multiplying the denominators in the summand results in the sum from I equals 1 to 10 of 1 over 5 plus x minus 1. So now let's go to the calculator and calculate that sum. We go to the list menu to retrieve the sum and sequence functions, just as we did before. And now we press enter. We find that this S10 is equal to 1.168. Now let's compute the midpoint approximation with n equals 10. Here, x hat sub I is going to be 1 plus I minus 1/2 times 1/5, and the corresponding S10 is the sum from I equals 1 to 10 of 1 over that x hat sub I times 1/5. This simplifies to the sum from I equals 1 to 10 of 1 over 5 plus I minus 1/2. And again, go into the calculator, we enter the formula, and find that that S10 is 1.097 approximately. Now let's calculate the right endpoint approximation with n equals 10. Here, x hat sub I is simply 1 plus I times 1/5. And so S10, for this choice of x hat sub I, is just the sum from I equals 1 to 10 of 1 over 1 plus I times 1/5 times 1/5. That summand simplifies and gives us the sum from I equals 1 to 10 of 1 over 5 plus I. So we go to the calculator and compute that sum and find that it is 1.035 approximately. Now let's do this again with n equals 40. Here delta x will be 3 minus 1 divided by 40, which is 2 over 40, or 1/20. For the left endpoint approximation, x hat sub I will be 1 plus I minus 1 times 1/20, and S40 is the sum from I equals 1 to 40 of 1 over x hat sub I times 1/20. We simplify as before, and we go to the calculator, compute the sum, and find that it's roughly 1.115. Now let's compute the midpoint approximation with n equals 40. Here, x hat sub I is 1 plus I minus 1/2 times 1/20. Here's the corresponding S sub 40. Here's the simplification. Here's the computation. And so we arrive at 1.0985. Finally, the right endpoint approximation with n equals 40 involves x hat sub I equals 1 plus I times 1/20. Here's the corresponding sum, S sub 40. And again, we simplify a bit, go to the calculator to compute the sum, and we find that this S sub 40 is 1.082. In general, midpoint approximations give us better results. The best approximation we have so far is the midpoint approximation S sub 40, which is 1.0985. So now let's try to get an idea of just how accurate that is by going to the calculator and computing the midpoint approximation corresponding to 200 rectangles. Rounded to 5 decimal places, that's 1.09861, which agrees with the midpoint approximation using 40 rectangles to 3 decimal places. Now let's go ahead and calculate the midpoint approximation with 400 rectangles. Rounded to 5 decimal places, we get 1.09861. So we see that these two midpoint approximations, first with 200 and then with 400 rectangles, agree to 5 decimal places. So we can be confident that those are correct and that the exact area of the region is 1.09861 rounded to 5 decimal places. Lower and upper sums. For a continuous function, it's always possible to choose our evaluation points so that our rectangles lie strictly underneath the curve. To do this, we simply let x hat sub I be the place at which the function has its minimum value over the corresponding subinterval. Such rectangles are called inscribed rectangles, and the corresponding sum is the nth lower sum for our function on the interval AB. Similarly, we can choose our evaluation points so that the tops of all the rectangles are above the curve. To do this, we simply let x hat sub I be the place where the function attains its maximum value on the ith subinterval. These are called circumscribed rectangles, and the corresponding area approximation is the nth upper sum for the function f on the interval AB. Now let's make some observations related to upper and lower sums. First of all, it's easy to see that any lower sum gives an underestimate of the area, and any upper sum gives an overestimate of the area. So for all n, the area is between L sub n and U sub n. Moreover, this is true even if we aren't comparing the same number of rectangles. In other words, every lower sum L sub n is less than or equal to the area, and the area is less than or equal to every upper sum U sub n, and so every lower sum is less than or equal to every upper sum. Now suppose we use a uniform grid. We can say that L sub 2n is greater than or equal to L sub n. In other words, if we double the number of rectangles, we can only increase the value of the lower sum. Here's a picture to illustrate that. Here's a lower sum L4. Notice that the height of the fourth rectangle is 0. Now let's double the number of rectangles to 8, and it's clear that the total rectangle area has increased. In fact, we can superimpose the two sets of rectangles to make this even more clear. Similarly, if we double the number of rectangles, then the upper sum can only decrease. Here's a picture to illustrate that. Here's an upper sum using 4 rectangles. By doubling the number of rectangles, we end up with a lesser total area. Now, by the previous observation, the area is trapped between all of those upper sums and lower sums. So what this tells us is that by doubling the number of rectangles successively, lower sums will tend to increase toward the value of the area, while upper sums will tend to decrease toward the value of the area. So what's happening is that the area tends to be squeezed between the lower sums and the upper sums as we let n get larger and larger. Now another observation is that regardless of how we choose our evaluation points x hat sub I, the resulting sum s sub n will be trapped between the lower sum L sub n and the upper sum U sub n. What this tells us is the following. Assuming that we know that the lower sums and the upper sums are approaching the same value as n goes to infinity, every other sequence of area approximations will approach the area as well, regardless of how we choose our x hat sub i's. Now let's look at an example. Let's let f of x be the cosine function on the interval 0 to pi over 2. For any choice of n, our delta x will be pi over 2 divided by n, or pi over 2n. Because this function is decreasing on the interval, right endpoint approximations will provide lower sums. In fact, L4 will be the sum as I goes from 1 to 4 of cosine of I times pi over 8 times pi over 8. L sub 8 is the sum as I goes from 1 to 8 of cosine of I times pi over 16 times pi over 16. L16 is a similar sum as I goes from 1 to 16. And L32 is a similar sum as I goes from 1 to 32. Now let's calculate these numbers. This time we'll use our TI-92 calculator. Here you see the command that will compute L4, which turns out to be about 0.79. Here's the command that computes L8. That's about 0.8986. This computes L16, 0.9501. And this computes L32, 0.9752. Now again, because the function is decreasing on the interval, left endpoint approximations will provide upper sums. Here's the picture for U4. U4 is the sum as I goes from 1 to 4 of cosine of I minus 1 times delta x, which here is pi over 8, times pi over 8. Here's the 8th upper sum, the 16th upper sum, and the 32nd upper sum. Let's go to the calculator and compute these numbers. The first one is 1.1835. U sub 8 is 1.0950. U16, 1.0483. U32 is 1.0243, where we've rounded all of our numbers to 4 decimal places. So notice here that as n increases, the lower sums are increasing and the upper sums are decreasing. And in fact, the actual area is going to be greater than all of the lower sums and less than all of the upper sums. Now let's continue with the same example, but this time we're going to make a very special choice of our evaluation points x hat sub I. In general, an area approximation with n rectangles has the form Sn equals the sum as I goes from 1 to n of cosine of x hat sub I times delta x, where delta x, remember, is pi over 2n. Now, we're going to use the mean value theorem to choose our x hat sub i's. Since cosine is the derivative of sine, the mean value theorem tells us that in each subinterval there exists a number x hat sub I so that cosine of x hat sub I is equal to sine of the right endpoint xi minus sine of the left endpoint xi minus 1 divided by delta x. And since delta x is equal to pi over 2n, we have cosine of x hat sub I equal to sine of xi minus sine xi minus 1 divided by pi over 2n. So now we substitute that value of cosine x hat sub I into our sum, and a minor simplification results in the sum from I equals 1 to n of the sine of xi minus the sine of xi minus 1. Now let's write out a few terms of that sum. The first term is the sine of x1 minus the sine of x0. The next term is sine of x2 minus sine of x1. The third term is sine of x3 minus sine of x2, and so on. And the last term is the sine of xn minus the sine of xn minus 1. Now let's notice that this simplifies a great deal. We have sine of x1 minus sine of x1, which equals 0. We have sine of x2 minus sine of x2, which is also 0. We have sine of x3 minus the sine of x3, and so on, until finally we have sine of xn minus 1 minus the sine of xn minus 1. So the only remaining terms are minus sine of x0 and sine of xn. A sum of this type is often called a telescoping sum. Notice that the only thing remaining after cancellation is a portion of the first term and a portion of the last term. So this very special Sn is equal to the sine of xn minus the sine of x0. Now let's recall that xn is the right endpoint, pi over 2, x0 is the left endpoint, 0, and so we have sine of pi over 2 minus sine of 0, which equals 1 minus 0, or 1. So for all n, with this special choice of x hat sub I, we have Sn equal to 1. And so we can say that every lower sum is less than or equal to 1, every upper sum is greater than or equal to 1, and therefore the exact area must be 1. Now let's think about what that last example illustrates, and this is a preview of things that are to come. Suppose that f of x is greater than or equal to 0 for all x in the interval a, b, and we want to find the area under its graph over that interval. If f of x is equal to the derivative of some function capital F of x for all x in that interval, then by choosing x hat sub I, so that f of x hat sub I is equal to capital F of xi minus capital F of xi minus 1 divided by delta x, which we can do by the mean value theorem, results in a sum, Sn, equal to the sum from I equals 1 to n of f of xi minus f of xi minus 1, which is a telescoping sum that simplifies to simply f of xn minus f of x0. And since xn is b and x0 is a, we have f of b minus f of a. So, f of b minus f of a, which is independent of n, is between every lower sum and every upper sum, and consequently that must be the exact area. So now let's look at a simple example. Let f of x equal x squared, and let's compute the area under the curve between 0 and 1. We'd like to know a function whose derivative is x squared. It's not hard to think of one. X squared is the derivative of 1/3 of x cubed, which is very easy to verify. And so the area under the curve is the value of that function at 1 minus its value at 0. So we have 1/3 of 1 cubed minus 1/3 of 0 cubed, which is equal to 1/3. And so the area under the graph of y equals x squared over 0, 1 is exactly 1/3. So notice that the region under the curve occupies exactly 1/3 of the square in the figure here.